here for a roll. And as I mentioned before, I think because of the first quiz and a little extra time explaining everything, what we're going to do is we're just going to kind of flop the days here in terms of the lab. So scheduled today was group 1, qualitative analysis. And that'll give us a little bit more time, hopefully on Wednesday, to kind of talk about the whole idea of qualitative analysis a little bit more, and then actually do experiment 5. So originally scheduled for this coming Wednesday was just like a kind of a little bit more lecturing. So that's what we'll do. We'll continue on here with 14, just kind of flop that lecture day to right now, and then we'll kind of work on obviously experiment 5 on Wednesday. So also a reminder, there's kind of a question earlier as well, somebody had. Again, after experiment 5, which was supposed to be done today, I think there's a little break in pre-labs, and that's really because next week I think we have a holiday on Monday, and then right now, as of now, scheduled a week from Wednesday is our first exam. So we wouldn't pick back up, I guess, with labs until probably, I guess it'll be 2 weeks from today, I guess, officially. So that's why there's a little lag in terms of the pre-lab when the next one's due and stuff like that, because I think we ran into a holiday, and again, our exam I think is scheduled come a week from Wednesday. Any questions on any of that there?
Are we gonna have lecture on Thursday?
We are on Wednesday, I think we'll. Yes.
Sorry, on Wednesday.
Yeah. So we're going to be lecturing now, and then we'll lecture like normal on Wednesday, and then normally what was scheduled on the syllabus and the schedule for this coming Wednesday was another lecture during lab time. So we're just going to kind of flop that. So we're going to do the lecture now instead of next Wednesday, and that'll give us more time to do the actual lab on Wednesday, because it might take a little bit more time on Wednesday, because it's qualitative analysis, so it'll give us a little more time to talk about sort of what that is and what you should be looking for in your videos. You'll be able to do your group 1 and group 2, group 1, known and unknown. Other questions? Okay, so we've been talking about KAs now with weak acids and how to work those. And really, as we saw at the very end there, it's essentially just an equilibrium problem. We work it the same way, which means if we can make an assumption, we could do the assumption. If we can't make the assumption, obviously we can't do it. We need to do the quadratic formula. But the major difference, as I mentioned earlier, was usually we're interested in everybody's concentration or pressures at equilibrium. But here, in the case of a weak acid, we're normally just interested in the H+ concentration, because that will allow us to get to the pH of the solution, which is ultimately what we're sort of looking for. So I think it's where we left off here. So why don't you give this one a go? And while we're at it, why don't we also calculate the pH on this one just to make sure? So in addition to the H+, also calculate the pH. And while we're at it, we should know it's acidic, I think. So what is the pH? So take a couple minutes here, and then we'll go over it, calculating this one. Help you if you're not sure. So a lot of times, a very common question people oftentimes ask is like, how do I know this is perhaps a weak acid? Again, the super big hint is right here. Again, we see a Ka value. As soon as we see that, that automatically tells us that this thing is weak, and we should be doing some type of ice table to solve it. So again, you don't want to overlook a lot of information that's sort of given to you in the problem. Like in this one, they didn't just straight out say, hey, this is a weak acid or something like that. But again, by seeing that value, that gives you a fairly good idea of what you're dealing with. And because it is a weak acid, as I mentioned, we do need to do an ice table. So we simply just want to start with it breaking apart. Again, if you want to include the water on the left-hand side, you can. You'll just get H3O plus, or you could just do it like I'm doing here, just simply showing it breaking apart. Initially, again, we're only given the 0.01. That also means we can initially assume zeros for these guys. We're going to also assume it's going towards the product side because we weren't given any information, which gives us our normal sort of minuses on the left-hand side and pluses on the right. Going to equilibrium will bring everybody down. Any questions on the ice table here? So if we write our Ka expression, it is our products divided by our reactant in this case. and that is going to equal what they gave us, which was 6.2 times 10 to the minus 10. Putting in our equilibrium line there gives us x squared 0.01 minus x equals 6.2 times 10 to the minus 10. That's a fairly small number there. So for our k value, so we can take a assumption here that x is equal to 0. And if we do that, that would then reduce us down to x squared divided by 0.01 is equal to 6.2 times 10 to the minus 10. We're going to multiply the 0.01 to the other side. We also want to make sure we take the square root of it. And we do all that good stuff, square rooting it. It looks like we are going to end with something like an x value of 2.5 times 10 to the minus 6. Because we did make the assumption, we want to make sure it's okay. So we would take 2.5 times 10 to the minus 6, which is basically the x value that we got. We would divide it by what we were going to subtract it from, which is really the initial concentration, and times about 100. And in this particular case, we are nowhere even near 1%. It's like 0.02%, which means that this check is good. And that also means that this should also equal our H plus concentration, which also means we need a molarity there. Any questions on that so far? Once we have our X value, which is really our H plus concentration, we could also answer what I asked you to answer in addition, which is the pH. So we would take minus the log of 2.5 times 10 to the minus 6. And looks like we do get like a 5.60 as our pH value. Does make sense. It is an acid. So we do have a pH value of 5.60. Any questions on any of those, or are you calculating weak acids? So the good news is, like I said before, pretty much same calculation. Only additional thing is probably got to use your pH equation at the end. Otherwise, you pretty much proceed very much like everything else that we've been doing. Any questions? Everybody's good on that? Yeah. Okay, then let's talk about acids in another sort of, I don't want to say situation, but sort of what's happening with acids. Which is what is sometimes referred to as percent ionization. So percent ionization, percent dissociation, these are all fancy words, I guess, for, how much of it breaks apart, right? So if we have pretty much an acid, just a generic sort of acid here, we're really looking at when we talk about percent ionization is really how much free H plus compared to the original concentration that we got. So to calculate the percent ionization, we take the amount of H plus concentration divided by the initial times 100%. It is essentially how we do our checks. So all those checks that we do when we make our assumption, that's basically how you calculate the percent ionization. So in the last example there, we have the 2.6 times 10 to the minus whatever it was there, 5 or 6, and we divided by our initial concentration times by 100. That's essentially what we're doing when we calculate the percent ionization. H plus concentration, which is how much of it broke apart. Initial concentration, that's what the little knot on the bottom there means, or 0, is our initial concentration. And the difference is when we do have a strong acid, as we talked about, 100% of it breaks apart. So you pretty much have ions all the way through. When we're dealing with a weak acid, because it's a reversible type reaction, the concentration does make a difference in terms of the percent ionization that's going to occur. So what that means is if you look way down on this side, as the concentration increases, the percent ionization decreases, right? And vice versa, as the concentration is down in this end, concentration gets smaller, the percent ionization increases. And that's why in certain cases, your assumption will work. And in certain cases, your assumption may not work. So if you go back to those two examples we looked at earlier today, I think it was one was like 0.5 molar, like it was what we were doing there, HF, I want to say. And then it worked, it was okay, the assumption. But if you remember when we just kind of went to the 0.05 molar HF, the assumption was bad. It didn't work, right? And that's because the real truth is there's a difference in those concentration values. And it's sort of like, a pizza example per se, right? If you get a brand new pizza, maybe I had one yesterday during the Super Bowl, but if you take one pizza out of the pizza, you still have a lot of percentage of your pizza still there, right? You haven't lost a lot. But then what always happens when you order a pizza, right? There's only like 2 slices left, right? And nobody wants to take it because there's only 2 slices left. But if you take one slice out, if you only started with 2, that one slice that you took off is like 50% of what you just had there. And it's a much bigger percentage. So that's the same idea that we see here with sort of percent ionization, and really why in certain cases, that assumption works. In other cases, it doesn't. It has a lot to do with the concentration of your acid to begin with. And again, if you have a fairly large concentration, that little bit that comes off is not going to make a tremendous difference, but you're not going to have a big change that will occur. But if you started with a really small amount and you lose a small amount, it's going to be a bigger percentage of where you started with. And that's sort of the idea of what we talk about is percent ionization. And again, why in certain cases, that assumption works. But if you change the concentration, like we see here, in that earlier examples we looked at, we had 0.5 versus, 0.05. When we lose a little bit out of here, not such a tremendous big deal. It was like 3%. When we got to here, we ended up with like 12% difference. And it was a lot larger of a difference that occurs. And that's really because we were starting with a much smaller concentration. Any questions on that? So let's take a look at one of these here. We have a solution that is 8 molar formic acid and is 0.47% ionized. Here we actually want to figure out what is the value of the Ka. So we do have some options there, but let's take a look at it together here, how we could get there. First off, if we did a sort of our ice table here, we would have our formic acid. It would break apart into H plus and some formate. By the way, I know it's a weak acid because I'm looking for a Ka value, right? So that's a very big hint that we're dealing with a weak acid in this particular case. And if we were to write our Ka expression here, it would be the concentration of our products divided by our reactant in this particular case. And this is actually what we are trying to figure out. So we could kind of use an ice table like normal. So if we start our ice table, we were told we started with 8 molar of this guy. We really weren't told anything about this guy. We do our change, it would be minus X, plus X, and plus X. And if we get to equilibrium, 8 minus X, X, and X. Now, normally at this point, when we do an ice table such as this, we then go into this expression and solve for X. But clearly we cannot do that at this point because that's ultimately what we're trying to find is the Ka value. So we use this piece of information. So we could actually use the percent ionized information to basically help us out and solve really sort of this ice table backwards. So what we just saw was that the percent ionization is equal to the H plus concentration divided by the initial concentration of our acid, which in this case is this guy, times 100%. That means that if we put that in there, we have 0.47% is equal to H plus over 8 molar times 100%. If we solve for H plus, what we will end up with is 0.47 times 8 divided by 100, 0.0376. Any questions on that so far? So you may be saying to yourself, why would it be sort of important to figure out, what is that H plus concentration? It's important because if we go back to our ice table, we could see that the H plus concentration at equilibrium is equal to X. So now that I know what my H plus concentration is, I know what this X is, I know what this X is, very much like that experiment we did. And this is 8 minus X here, if I wrote it right. I know what this X is as well. So sort of by using the percent ionization, it allows us to really figure out what is the equilibrium concentration of H plus. And because in our ice table, that equals X, that allows us really to figure out what X is in that table. Any questions on that? So ultimately what that tells us is the H plus concentration equals X. That also equals the HCOO minus concentration. And both of those guys would have a concentration of 0.0376 molar. The table also tells us that the concentration of formic acid at equilibrium is 8 minus X, which tells us it is 8 minus 0.0376. And that gets us 7.96, we'll call it, molar. And now we have all three of these guys is equilibrium concentration. So we could actually stick it in there and we would have 0.0376 times 0.376 divided by 7.96. And if we do all that good stuff there, we end up with an answer of about 1.8 to the minus 4, it looks like. And that looks like perhaps it is choice. Question on that. So here we could use something like percent ionization to figure out the actual Ka value by working backwards. Again, very similar to what we did kind of in that experiment. I think it was maybe experiment 4, the one we did, or 3, one of those, actually experiment 3. Any questions on any of those steps? Okay. So that takes care of sort of weak acids. In addition to weak acids, we oftentimes will deal with weak bases. The good news is pretty much weak bases are worked the exact same way as we can work weak acid problems. The only difference is because we will produce over here hydroxide rather than H plus. And that means that we could get to the POH first and then get to really the pH at that point. So we can write an equilibrium expression just like we could do for our weak acids, which is our products over our reactants. Again, as I mentioned earlier, the water is oftentimes included in these sort of equations, but again, because it's a liquid, it is not included in what is known as our Kb value. So B for base, again, very creative, but it is obviously a Kb value. These are for weak bases. Strong bases will not have a Kb value, again, because they 100% break apart into ions. And same idea, as the Kb value increases, the strength of that weak base increases. Again, it's not as strong as a strong base, but it's strong in comparisons to another weak base. So we work these the same way. Sort of an additional step usually. Again, instead of at the end going into the pH, you need to go into really the POH and then subtract 14 and get to the pH value at that point. Any questions on that? So we do have a Ka that we saw with our weak acids. Do you have a Kb value? Sometimes people are confused as to, which one should I use, right? Or, which one should I be using? And again, it comes down to looking at these equations and the reactions properly. And if you look on the product side and you see some OH minus and you need to do some type of calculation, again, you should be using a Kb value. If you look on the product side and you have H plus or H3O plus, you should be using a Ka value for your calculation. Now, there will come a time in this chapter where you need to make the right choice on that, and that is the best way to figure out which one you should be using, because there are going to be problems where they will give you the incorrect K value. So they'll give you the Ka value, but in order to solve the problem, you actually need the Kb value and vice versa. So there are going to be some problems coming up where potentially they sort of give you the wrong value, and you need to be able to recognize that. Any questions on that? Okay. So this is a table Kb values. Again, would obviously be provided for you, but there are certain problems where you might have to look it up and verify it. So why don't you take a couple of minutes here and work on this one here. We're looking for the pH of this solution, the Kb values given to you, see what you come up with, and then we will talk about it in a couple of minutes. So again, approach it the same way as you did your weak acid, but again, it's a weak base, so see what you come up with. See how we're doing. So a couple of things from the problem here. Obviously, we see a Kb. So that tells us, obviously, this guy here is a weak base, even if it didn't tell us any of that. So that's important, again, when we think about sort of, what the equation should look like or the reaction should look like. So we have C2H5NH2. Since it's a base, that's usually a good one to include the water in. And again, this guy is going to basically give the H plus over. And we just simply can add an H plus there at the end if you like. But more importantly, this is what we should be producing on the product side. And again, it's really important to know how to write these equations. That's where a lot of people do struggle. And some people will end up with like H plus, H3O plus, which is incorrect. And that leads to other problems down the road, like you end up with like a pH rather than a POH and those type of things. So, really important to make sure you understand how to sort of write these things sort of correctly. We're going to do an ice table. Obviously, it's weak. So this is the only thing that's given to us. This guy would be 0 and 0. Change here would be minus X, plus X, and plus X, which means when we get down there to the end, 0.15 minus X, X, and X. Any questions on the actual ice table there? You may also notice that I did not do anything here. And again, that's because water, right, is not involved in equilibrium expression. And always a good idea to leave off things that, you might want to use in calculations and you shouldn't. So, best not to put numbers there and accidentally want to try to use it somewhere. We could write our Kb expression for this, which would be our products. Divided by our reactant. And again, the water not included here. And that equals our 5.6 times 10 to the minus 4. We could put our numbers in, gets us x squared over 0.15 minus x equals 5.6 times 10 to the minus 4. Again, this is a small value, so you can do your assumption here that x is equal to 0. If you did that, you probably found out it was a bad assumption here. I think it was like 6.1%, something like that. Again, over the 5% when you did it. So again, if you assume that x was 0, you went through this process here and solved for x. Hopefully, again, you checked it, and you would see that, again, it's above that 5% sort of limit that we put on it, which means, we really can't do it this way in this particular case. We will have to go back here and use the quadratic. Any questions on that there? Okay, so to do the quadratic, we need to take the bottom there, multiply it to the other side, combine everybody. So if we do that, we have x squared is equal to 0.15 times 5.6 to the minus 4. That gives us 8.4 times 10 to the minus 5, and then that would be minus 5.6 times 10 to the minus 4x. Bringing everybody to one side, going to get us x squared is plus 5.6 times 10 to the minus 4 minus 8.4 times 10 to the minus 5 is equal to 0, if I am not mistaken there. That obviously will go into our x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And again, sort of putting in some of those numbers there. Clean up some of that little scribble. Try that. It's going to give us minus b, which would be minus 5.6 times 10 to the minus 4, plus or minus, if we do the square root there, we have b squared, which is 5.6 to the minus 4 squared, minus 4 times a, which is 1, times c, which is minus 8.4 to the minus 5. Looks like perhaps we get something like 3.36 times 10 to the minus 4 inside, and square root 1.83 to the minus 2 on the outside. And that would all be divided by R2, basically. Going to give us 2x values. Doing the positive first, that's going to be minus 5.6 to the minus 4 plus 1.82 to the minus 2 divided by 2, giving us an x value of 8 looks like maybe something like 8.82 times 10 to the minus 3. Or again, if we went negative and negative, will get us a negative number, which we can't have either. So this guy should be our positive value there and our correct value for x. Any questions on that there? Okay. So do that. That means that x does equal the OH minus if we look at the table, and that will allow us to calculate the POH, which is minus the log 8.82 times 10 to the minus 3. It's going to be 2.05 looks like. And our pH will end up being 14 minus 2.05. Gets us an 1195, looks like, in terms of our pH value here. Does make sense. That is basic, and we're dealing with a base, so we would expect it to obviously be basic in this particular case. Any questions on any of those steps there? We got those numbers, hopefully, yes. Any questions on weak bases in general? So again, weak base problems, pretty similar to everything else we've been doing. Again, the main difference there, we get the OH minus rather than the H plus at the end. Main problem most people have, to be honest with you, with bases is just that no idea how to correctly write sort of the equation. So you do end up with some people that end up dealing with bases, but are writing equations that are acid equations. And again, that doesn't turn out right. So super important to me to write it correctly. And second major problem that most people have on these type of calculations with the bases is they get that number, that X value at the end, and they think it's the H plus concentration and they go right into the pH. So those are two very big areas where people do make a lot of mistakes. Any questions on that? Okay. So as we talked about before, when you should use a Ka, when you should use a Kb value, and again, this is the biggest hint that you will see along the way is really what you have on the product side. So as I mentioned many times at this point, if you see H plus, you probably should be using that Ka. If you see OH minus, you should be using that Kb value. Just like two equilibrium equations, if we actually add them together, we will actually get this reaction here. As the A minus is canceled, the HA is canceled. We actually get water, which we also saw as an equilibrium expression, which is Kw. So this creates a very good way to go from Ka to Kb if you need to. And there definitely will be problems where you'll need to do that. And that is that the Ka value times the Kb value equals Kw. And for the most part, like we talked about with Kw, that is our 1 times 10 to the minus 14 number that we saw earlier. So you could pretty much use that to get to the right one that you need. And as I mentioned before, it's basically the same calculation. Take 1 times 10 to the minus 14 divided by either Ka or the Kb value. But it's super important, especially when we start talking about salts. Those are very common problems where in the actual problem, they'll give you the Ka value, but to solve it correctly, you need like the Kb and vice versa. So this relationship is a very good one. It allows you to get to the number that you need very easily and a little bit and fairly quickly to calculate what you need in those particular problems. Any questions on that relationship there? So we're going to go next, though, is I think we're going to skip around a little bit on the notes. So we're going to come back to us next. So I think on your notes, you have something like polyprotic acids and stuff like that. So we'll come back to that. We're going to actually talk next about acid strength. So you could also find this in your notes. It's just in the next little part. So we're going to talk about acid strength. And there's really two types of acids we sort of talked about. And that is ones that have oxygen and one that does not. So this, when we're comparing two acids that do not have oxygen, you may be tempted to think, well, maybe what I should look at here is electronegativity. And if you remember what electronegativity is basically the ability of an atom to bring electrons towards itself. And the higher the electronegativity, you might think, well, that means electrons are going this way, should weaken that bond. That's probably what I should look at. And it would be incorrect in this case. The overwhelming thing that we look at when we're dealing with this acid versus that acid, and they do not contain oxygen, is actually bond strength. So bond enthalpy is sometimes referred to. You might have talked about that when you talked about bonding in the Chem 1A. There's a certain amount of energy that's required to break a bond, right? Or a certain amount of energy required, when we release energy to make a bond, and a certain amount of energy required to break a bond, which is putting energy in. And if we look at the bond energy as you go through, say, group 7 here, which are pretty much our guys that do not have oxygen, our hydrofluoric acid, hydrochloric acid, and so forth down the road, we see that as we get to the top there where hydrofluoric acid is, it has a bond energy of 565 kilojoules, while if we get down here to HI, it actually has a bond energy of 295. So what does that mean? Well, that means that when we look at something like HF and we look at something like HI, in order to break that bond, you got to put in there 565 kilojoules of energy. In order to break this guy's bond, you got to put in there 295 kilojoules of energy. Because it takes so much more energy to break the HF bond, that means that less of it will come off and make H plus and F minus, right? It's a lot harder to get that to break off than it is when we look at our HI to break apart into H plus and I minus. What makes something an acid is the ability to generate H plus. So because it's a lot harder to break this bond than it is, say, this bond over here, the harder it is to break the bond, you're going to end up with less free H plus floating around. And because you have less free H plus floating around, it's going to be a weaker acid than something like HF, where you don't have to put as much energy in. You're going to generate more free H plus in the case of HI. So unlike electronegativity, when we look at these type of acids, bond strength decreases as you go down, and the strength of acids, especially in group 7 here, you can see strongest acid towards the bottom, weakest acid towards the top. So these three are strong acids. This guy is a weak acid. Again, a pretty good jump in terms of energy, almost 200 or so more in terms of kilojoules of energy. So that's why when we look at HF, it's a weak acid. The rest of these guys are strong acids. Any questions on that? So in comparison, again, like I said, of acids that do not contain oxygen, that is really the overwhelmingly thing you want to look at, which is bond enthalpy. If you have something that has a much higher bond energy than something else that has less, the one with the least amount of bond energy will be the stronger acid. And it basically just means it's a lot easier for it to produce H plus, which is basically the essence of what an acid is. Any questions on that type of acid? Now, the other type of acids that we talked about are really ones that are sometimes referred to as oxyacids, and they basically do contain oxygen. So acids that contain oxygen will usually have this bond right here. That's that OH bond. That is a polar bond, and that's what these guys represent. That is a partial negative charge. That's a partial positive charge. Those are delta, delta minus, delta positive. And that's because when you look at electronegativity, oxygen is more electronegative, which means the electrons in that bond are heading towards the oxygen side and potentially weakening that bond and allowing the H plus basically to pop off. And basically that's what makes it an acid. So most oxyacids contain those polyatomic ions. Most of those polyatomic ions contain at least one of those bonds, that OH bond, which is a very polar bond. So when we're dealing with this sort of acid here that contains oxygen, we really look at two different things depending on the situation. We may look at the central atom, which is sometimes appropriated there with a Z, and we may look at electronegativity, or we may look at something which is known as oxidation number to help us decide sort of which one would be a stronger acid when we're trying to compare two oxyacids to each other. So let's take a look at both of those situations. The first situation is one where we have an acid that the central atom is from the same group, but and they have the same oxidation number. So if we look at this guy here, our central atom is chlorine, and our central atom is Br. The part that makes it an acid in both of them is this bond right here. And what's going to make which one of these guys sort of the stronger acid is the one that's going to be able to release that H plus easier, basically. So first off, they are from the same group. If you look at the group there, group 7. And if we calculate the oxidation numbers, so hopefully you remember how to calculate oxidation numbers. If not, we will talk about a later chapter. but let me give you sort of the Cliff Note version of how we would get to the oxidation number here. Usually, if you're trying to calculate oxidation numbers, for the most part, oxygen carries an oxidation number of -2. Unless it's peroxide, then it's -1. So we would assign a -2 for the oxidation number for that oxygen, -2 for that guy, and a -2 for that oxygen. Hydrogen basically will have a +1 oxidation number. So if we add all that up, we have +1 for the hydrogen. We have basically -6 for all three oxygens. And if we do all that, that is a -5. This whole acid has no charge, which means in this particular case, the chlorine is carrying a +5 oxidation state in that case. Remember that oxidation states, as you might remember, and we'll remind it later on when we get to electrochemistry again, oxidation states are not necessarily the normal charge we think about when we think about an atom like chlorine. We normally think about chlorine in the ionic sense as a -1 charge, but in this case, it's not an ionic bond that's happening here, it's covalent bond. And in that particular situation, it is carrying a +5 charge rather than a -1 charge. So oxidation number or oxidation states are not exactly the normal sort of charges we associate with certain elements. So that's why, again, something like chlorine here would have a +5 oxidation number. Any questions on that? If we look over on the other guy, same sort of assignment, this would be -2. This guy would have a -2 oxidation state. This guy would have a -2 oxidation state. Hydrogen here has a +1, so we end up with the exact same situation. We end up with -5. The bromine here would be carrying a +5 oxidation state, just like the chlorine on the other side. So this is what it means by they come from the same group, the chlorine and the bromine. They both are carrying a +5 oxidation state, which means we cannot use the oxidation state of the bromine or chlorine to decide which one's going to be the stronger acid. So what we have to think about then is electronegativity. And again, electronegativity is the ability of an atom to bring electrons towards itself. And hopefully from 1A, you remember, if you look at the periodic table, electronegativity increases as you go this way, up and to the right, decreases as you go down and to the left in terms of electronegativity. You also might remember that our good friend fluorine is the most electronegative element that you could have. So when we look at these two acids and we want to determine sort of which one is stronger, we want to look at the one that has the higher electronegativity. So in the case between chlorine and bromine, chlorine is more electronegative, which means that this acid on the left should be the stronger acid of the two. So why is that? What is really sort of happening? Well, again, they both have this bond. This bond is, again, partially positive, partially negative. But when we get to our next guy here, our chlorine versus our bromine, we'll just draw that part of it. The electrons are already heading towards the oxygen in this bond. But because the chlorine is more electronegative, it's going to bring those electrons even closer to itself. And what that's going to essentially do is continue to weaken this bond and weaken it enough that this is going to come off easier than the same situation happening here. The bromine will bring those electrons towards itself, but not to the extent that chlorine will. And it is weakened, but not to the same extent as it would be with that chlorine and its electronegativity. And that would make here our HClO3 a stronger acid than our guy to our right because of electronegativity. So when dealing with oxyacids, acids that have oxygen, if the central atom is in the same group and it has the exact same oxidation number, it is the one with the higher electronegativity value that is the stronger acid. So basically, if the acid looks the same, except you have a different central atom, you want to look at electronegativity values. Question on that. All right. So what happens in sort of the opposite case, where we have actually the same central atom, but everything on the outside is sort of different, that involves basically acids that have oxygen. So if we have the same central atom, but everybody else on the outside is different, what we look at is not electronegativity, because obviously the central atom would have the same. We look at oxidation number. So all these guys have a chlorine as its center atom, which means obviously if we were going to compare electronegativity values, all the chlorines would be the same. So here in this case, because we cannot compare those things because the electronegativity is the same, we actually do look at oxidation numbers. So again, it's important to sort of know how to do it. If we look at the top here, oxygen again, -2. Hydrogen would be +1. That's a -1, which again means in this particular case, the chlorine in that arrangement is carrying a +1 oxidation state. We go to guide to the right, that is a -2 for that oxygen, -2 for that oxygen, +1 for that hydrogen. That is -4, and +1 is -3 to balance it out to 0. The chlorine in this case is carrying a +3 charge or oxidation state. This is the same one we did earlier, -2, -2, -2, and +1. That's going to carry our +5 oxidation state. And lastly here, -2, -2, -2, and -2, and +1. That is a -8, and +1 is a -7. The chlorine here carrying a +7 to balance that out. So what's happening here is the same idea. It is again that weakened OH bond, but when we get to the chlorine that has the +7 versus say the chlorine that has +1, the chlorine with the +7 is going to bring those electrons, opposites attract, much closer in, again going to weaken this bond a lot more and going to allow that H plus to come off and make it a stronger acid than say this guy over here, which again is still going to kind of bring those electrons in, but not as much, not going to weaken that bond more, and it's going to hang on to that H plus a little bit more than it normally would. Questions on how to identify sort of what acid is stronger, which one is sort of weaker based on different sort of characteristics? Questions on any of those there? So in this particular case, the perchloric would be the strongest, followed by the chloric, the chlorous, and then the hypochlorous acid, which has the lowest oxidation state, would be the weakest of those four. Any questions on that? So just a refresher on that, what we talked about, if there's no oxygen, you look at bond strength. If there is oxygen and everybody has the same oxidation number, you look at electronegativity. And if there is oxygen and everybody's the same central atom, you look at oxidation numbers. Okay, so let's then talk a little bit about salts and some of the properties that occur with salts. Salts, if you are familiar with, are really just a fancy word for an ionic compound. Positive and negative guy, right? Cation, anion that's coming together. We get salts really from the basic acid-base reaction, right? When you take an acid plus a base, that's basically how we generate salts. We get a salt plus some water. So usually the H plus from the acid and the other part from the base, in terms of the negative part, comes from the base. And that's basically how salts are basically generated. Now, certain salts will be developed and made and really not do anything to mess up the pH. They really won't continue to react. But there are other salts that when they are produced will continue basically to react, and they'll continue to react with water. So there are certain salts which are referred to as neutral salts, and these are salts that contain an alkali metal or alkaline earth metal, except for beryllium. So that's basically group 1 and 2 on the periodic table, and the conjugate base of a strong acid. So when we talk about salts, this is where that sort of opposite relationship is really important to understand. Again, as we talked about earlier today, if your salt comes from something that is strong, the conjugate partner of the salt will be weak. And if it comes from something weak, it will make something that is relatively strong. So again, that opposite relationship really important here. So when we get a salt like sodium chloride, it really is going to break apart into sodium ions and chloride ions in solution. So when we are thinking about something like sodium chloride as a salt, it is really a neutral salt, but we want to think about really kind of where these things came from. So if you were asked, like, what is the acid and base that both of these things that sodium chloride came from, you probably could figure out relatively easy, hopefully. If it was the sodium ion, it most likely came from sodium hydroxide. If it is Cl minus, it most likely came from hydrochloric acid. That is a strong acid. That's also a strong base. So again, where something like that would come from is HCl plus some sodium hydroxide, double displacement reaction, making sodium chloride plus some water here, right? Basically, these two guys switch partners, right? And that's basically where this salt would be generated from. Now, because the sodium comes from most likely sodium hydroxide is a strong base, which means this part of the salt is going to be pretty weak. The HCl, which is the strong acid, is going to basically donate that Cl minus into the play. And because that's a strong acid, its partner is going to also be relatively weak. And what that means is neither one of those things will continue to react. And we would expect the solution basically not to have a lot of free H plus floating around or a lot of free OH minus floating around. So we would expect the pH in this case to be 7, a neutral solution. Any questions on that there? Now, that's not always the case. So what happens if I take something like sodium hydroxide and react it with something like acetic acid, which is this? This is sodium hydroxide, which is a strong base. This is acetic acid, which is a weak acid. Also going to do really a double displacement reaction here. We're going to get some sodium acetate and some water going to be generated in this particular reaction. So the salt, which is this guy that's being generated, is really what we would want to sort of think about and see whether or not, it's going to continue on to react. And if we take something which is like sodium acetate, which is basically an electrolyte, a strong electrolyte, it's going to break apart into sodium ions and acetate ions. So this is basically the two parts of the salt that was generated if we sort of think about the reaction like one step back where it came from. Also really important is if we think about the two parts of this, we have sodium here. The sodium ion, just like we says up here, is really a neutral ion. It's not going to do anything to affect the pH of that solution. We know that really because we can make a pretty educated guess that that sodium ion that's in that solution basically came from sodium hydroxide, which is a strong base. which means that its partner, which is the sodium, would be relatively weak. So in terms of any type of further reaction that's going to occur, the sodium part of this, we don't really have to worry about because it basically comes from something that is strong. Any questions on that there? That leaves us one other part of the salt that may be able to react with water, and that is the acetate part. Now, the acetate part comes from acetic acid, which we know is a weak acid. And if you don't know that, you will definitely know that because it's a very common example used in a lot of things in terms of weak acids. But because this is a weak acid, its partner here is going to be relatively strong. And what that's going to tell you is when you produce a salt like sodium acetate, or you have a salt like sodium acetate, in that little beaker, what's floating around is, if you want to kind of simplify it, three things. You have sodium ions that are floating around, you have acetate ions that are floating around, and you really have water that's floating around. So we already know that the sodium is not going to do anything. But because the acetate is relatively strong, it will then go and find our good friend water, which is also floating around in there. And what will happen is the acetate will then continue to react with the water. And what's going to happen is we're going to get the acetate reacting with the water, which is sitting in there floating around. And what's going to happen is we're going to get a reaction that's going to occur. Now, this is also the part that people get trouble in because they're not really sure how to write this reaction or really what is going on. So let's talk about how you could kind of think about it. If we just think about where acetate came from, it came from a weak acid, which means its partner would be a conjugate base, right? So since acetate really came from acetic acid, which is an acid, it being its partner on the other side of the equation, basically, right? It's on the other side of the equation. It will act as a base. And that's really important because when we get down here, where the acetate is reacting with water, is going to react as a base. And we know that a base is something that will accept an H plus, right? So it's actually going to pick up the H plus from the water. When it does, we will make acetic acid and we will make OH minus. A couple really important things to know how it sort of always occurs. We just made on the other side, when the acetate reacted with water, acetic acid, we basically made where it came from. And that's always the case, right? So we know that that acetate came from acetic acid. When it reacts with water, we're going to make where it came from, which is acetic acid. And that's how we get there. Also, really, just the H plus going over. But more importantly, what this tells us is we just produced OH minus in this reaction, which means if we go back to our beaker, by those two reacting, we're starting to generate more OH minus in that beaker from that reaction. And what happens when the concentration of OH minus increases? The pH should go up, right? Because the concentration of H plus goes down. And what we know is without even doing one little calculation at all, we know and we can make a very educated guess that this solution we're dealing with, like in this beaker, this solution here should be a basic solution because we generated OH minus. Any questions on that? Now, these salt questions are the questions where they will historically give you the wrong K value. And if you had a problem like this where it asks you something like, hey, what is the pH of a 0.5 molar sodium acetate solution? They would probably give you the Ka value for acetic acid. And this is where it's important what we talked about earlier. When you write this equation properly and you see the OH minus over here, and you need to do a calculation, that should scream to you, I should be using a KB value. And I can't tell you how often people will use a Ka value because they were given it in the problem, and they don't realize that they actually need to figure out what the KB value. And to figure out the KB value, that's where you would use that Ka times KB equals Kw. So salt type problems are historically ones where in the actual problem itself, they oftentimes will give you sort of the Ka value when you need to calculate the Kb value and vice versa. Any questions on this? This is considered a basic salt, which I think is what you have written down on your notes there before I started scribbling. This would be a basic salt. Any questions on any of that there? Okay. So there's also acidic salts, and acidic salts, I'll put that in there. That should be on your notes though, but it's basically what we just talked about. There's also acidic salts, and these are salts that are derived from a strong acid and a weak base combination. So again, if we took something like HCl, which is a strong acid, and we react it with a weak base like ammonia here, that's a weak base, we will end up with something like NH4Cl, basically. And basically, he's going to donate over. It's really going to make NH4 plus and Cl minus. A lot of times people will combo those guys together. Now, when we look at this salt, as I just wrote, it is basically, when it's in solution, ammonium ions floating around and chloride ions floating around. So in this sort of beaker, if you want to think about it, you got some NH4 guys moving around. You got some Cl minuses floating around. You also got some water still floating around as well. So in evaluating the salt, we want to kind of do the same thing as what we did on the previous one. Is whenever you're dealing with a salt, you want to look at both parts of the salt, the cation, the positive guy, and the anion, right, which is the negative guy. And you want to determine really kind of where they came from and will they continue to react with water. So we could really eliminate something right off the bat, which is our Cl minus. As we saw on the first one, Cl minus, as we can see in this reaction, comes from a strong acid, which means it's going to be relatively weak. And what that means is it is not going to react with water and really mess up the pH. It's basically going to be neutral. Now, when we look at the NH4 plus, which is ammonium, we see it comes from ammonia here. Ammonia is a weak base, which means this is going to be relatively strong. Now, it came from a weak base, which means this conjugate partner is going to be relatively strong, and the partner of a weak base would be something that will behave like a acid, basically. And what's going to happen is the NH4 plus will then start to react with the water that's in there, the Cl minus, really not going to do anything. And when those two come together, we get NH4 plus plus some water here. It's going to act as an acid, which means it's actually going to donate the H plus over. When it does, we will produce H3O plus, and we will also, just like with the acetic acid, produce where it came from. So the NH4 plus will then kind of go back, if you will, to sort of its origin, where it came from, and make ammonia. Any questions on that part of it? So why is this important when we look at this reaction as to what is going on? It's important because we are now generating a bunch of H3O plus, which means we would expect this guy, without doing a calculation, to be acidic, because in our beaker here, we're now making a bunch of free H3O plus basically floating around. And again, same idea. If the concentration of H3O plus, which is the same as H plus, increases, we would expect the pH to decrease. And if the pH decreases, that solution should be acidic in that particular case. Also means, right, the OH minus is decreasing as well. And it would make an acidic solution. And important in terms of a calculation is we would expect it to be a Ka value that we need to use here when we see that H3O plus basically being formed. Any questions on that? So one way that we get really an acidic solution from a salt is from a combination of a strong acid and a weak base. There's actually another way that you could kind of get an acidic solution to happen from a salt, and that's from metals that have a high positive charge. So some metals with a high positive charge can really be considered sometimes acidic salts. An example would be the one you have on your slide. I'll just write it, something like this. 6 and that. And ends up with something like this. And again, I think this is on your notes there. So what we really have here, this is was referred to as a complex ion, and you'll know how to name it by the time the class is over. But for a lack of what's really sort of happening here is what we essentially have is, let me erase some stuff here, get somewhere to write. Well, can I get rid of that right there? We basically have an aluminum that has a positive 3 charge in the middle, and attached directly to it is 6 waters. So basically got 6 waters. They would be attached by the oxygen, so ignore where I kind of draw the line, but they're attached to the oxygen. 1, 2, 3, 4, and 5. And on the 6th one, I'll just draw it out way over here. So I got some room. Not probably that long away, but we have basically a 6 water that's attached. And again, I just drew it over there. And what's going to happen in this particular case is when you got this metal basically floating around, and that's essentially what's happening when you put like something like aluminum there in water, is you have this floating around with a bunch of water sort of attached. Another water just by itself, not attached to aluminum, will come by and basically take off one of those hydrogens. And when it does, what it will produce is H plus or H3O plus. And if you just kind of keep track of everything, what you're left with is this really big guy, which you'll also know how to name. And if we just count everything that's left over, there's an aluminum, that's the aluminum. There's an OH, which is what is left after that H comes off. And there's basically 5 waters, right? So there's 1 water, 2 waters, 3 waters, 4 waters, and 5 waters. So that's what's left over when it's all said and done. So this is another way that we can make basically an acidic solution, is sometimes considered an acidic salt, is by these really small positively charged metals. A lot of times transition metals oftentimes can do it. Aluminum's common as well. But these kind of +2s, +3 sort of metals, copper as well, that has sort of that +2, +3 sort of range, can basically do this. So as they're floating around basically in water, these metals, they're really surrounded by water, but they also will sort of interact with water by itself and ultimately produce these H3O pluses, which would result in an acidic solution. So we have salts that are neutral where the pH would be 7. We have salts that are basic and will produce OH minus, and we would expect obviously the pH to be above 7. And there are salts like we see on this screen here that are acidic salts, and they will produce H3O plus or H plus, and we would expect the pH to be acidic. Any questions on any of those three sort of salts? So this is definitely the one where when we deal with salts, people have trouble, like I said, writing the equation. These are also the ones, like I said, that the Ka and the Kb, you oftentimes need to switch them using Kw. And then why it's really important to be able to write these equations correctly so that you know when you look at your product side, I see OH minus, I should be using a Kb. I see H3O plus or H plus, I should be using a Ka value. And again, that's really crucial to be able to do that. Any questions on any of that stuff there? All right, well, that seems like enough torture. Everybody's quiet, so I imagine maybe everybody's sleeping right at this point or something like that. We will wrap it for today, I think, and we'll continue lecturing. So I have a pretty good feeling we'll probably get through the rest of 14 maybe on Wednesday. So as it stands now, the exam is still going to be on Wednesday of next week, again with Monday being a holiday. And I'll let you know, obviously, for sure when we're done on Wednesday if it's going to be or not, or something's going to move. But just sort of tentatively looking at it, I think we will probably be still on pace and everything like that for it to be a week from Wednesday, the exam after the holiday. Any questions on any of that? Okay, other than that, if you didn't put here, make sure you put here in the chat box. Have a good day.